interior of a set in a metric space. Let X be an arbitrary metric space and let A be a subset of X. Then a point small x in A is called an interior point of A if it is the center of some open sphere contained in A. The interior of A is denoted by int of A, and it is the set of all its interior points. Symbolically, interior of A is the collection of all points x such that some open sphere SR of X is contained in A for some R. Basic properties of interiors. Interior of A is the largest open set contained in A. To prove this property, first we must prove that interior of A is an open subset. For this, let us consider an arbitrary point small x from interior of A. Then small x is an interior point of A. So there will exist some R greater than 0 such that an open sphere centered at X with radius R is contained in A. This condition is obtained from the definition of interior point. Since SR of X is an open sphere, it is an open subset of the metric space, and hence for any point Z of this open sphere, there will exist some R1 greater than 0 such that SR1 of Z is contained in SR of X. That is, since SR of X is an open set and since Z belongs to SR of X, there will exist some open sphere centered at this point Z and such that it is contained in this open set SR of X. So there will exist some R1 greater than 0 such that SR1 of X Z is contained in this open set, and we already know that SR of X is contained in A. So we have SR of R1 of Z is contained in A. That is, an open sphere centered at Z is contained in A. So from the definition of interior point, we can conclude that this point Z is an interior point of A. So SR of X is contained in interior of A. Thus we have proved that for any X element of interior of A, there exists an open sphere centered at X contained in interior of A. So from the definition of open sets, we can conclude that interior of A is an open set. Now we know that if X element of interior of A, then an open sphere centered at X will be contained in A. So obviously this point X, which is the center of this open sphere, is also contained in A. So X element of A. Thus we have proved that every point of interior of A will be contained in A. So we can say that interior of A is a subset of A. Thus we have proved that interior of A is an open set and that it is contained in A. So interior of A is an open set contained in A. Now it remains to prove that interior of A is the largest among open sets contained in A. To prove this, let us consider any open set, say U, contained in A. Then if X element of U, there will be an open sphere centered at this point contained in U. So there will exist some real number R greater than 0 such that SR of X, the open sphere centered at X, is contained in U. From the definition of open sets, since U is contained in A, we will have this open sphere SR of X will be contained in A. Thus we have proved that for any X element of U, there exists R greater than 0 such that SR of X is contained in A. So we can say that X is an interior point of this set A. That is, X belongs to the interior of A. Thus we have proved that every point of U belongs to interior of A. So we can say that U is contained in interior of A. So we have proved that interior of A is the superset of any open set contained in A. In other words, we can say that interior of A is the largest among open sets contained in A. Or interior of A is the largest open set contained in A. Second property states that if A is open, then A is equal to interior of A, and conversely, if A is equal to interior of A, then A is open. For the proof, let us first assume that A is equal to interior of A. Then obviously A will be open, as we have already proved that interior of A is open. Conversely, assume that A is open. We know that interior of A is the largest open set contained in A. Since A itself is an open set, this will be equal to A itself. Thus we have proved that interior of A is equal to A. Thus we have proved that A is open if and only if A is equal to interior of A. And this completes the proof of property 2. Property 3 states that interior of A equals the union of all open subsets of A. For the proof, let us consider the collection U, the collection of all open subsets of A. Then we have to show that interior of A is equal to the union of all members of this collection. Since interior of A is open and is contained in A, interior of A will belong to the collection U. Since the collection U contains all open subsets of, so we can say that interior of A will be contained in the union of all members of family U. Conversely, if X element of the union, then X will be a member of some member of the family U. That is, we can find some V element of the family U such that X element of V. V element of family U will definitely imply that V is open and V is contained in A. Since X element of V, where V is open, there will be some open spheres centered at X contained in V. And this inclusion together with the inclusion V is contained in A will imply that SR of X is contained in A. This means that X is an interior point of, that is, X element of interior of A. Thus we have proved that if X belongs to this union, then X will belong to interior of A. Conversely, we have obtained that union of the members of family U is contained in interior of A. Thus we have proved that interior of A must be equal to the union of all members of family U. That is, interior of A is equal to the union of all open subsets of A. This completes the proof of property 3.